soal. Okay, so chapter 4 is actually going to discuss, wait a minute. Okay, so chapter 4 actually is going to discuss, right, points on models and techniques for geometric modeling. So a lot of info and notes on chapter 4 is actually very directly linked with your lab work, because basically you're using CATIA for geometric modeling, and you would have gone through different modeling techniques like extruding, sweep, or in CATIA known as rib, and then after that shaft, which is revolve, and then multi-section solid, and many others to come, right? So all these things are actually modeling, geometric modeling techniques, all right, for 3D modeling. So we hope that you will understand this chapter better because you've already covered the aspects of modeling over there. Okay, so the whole idea of a geometric model, right? Why do we even require a geometric model? Okay, so what do we have? Just a minute, let me get the ink color. So why do we need this geometric model over here? Okay, so pardon my writing or my pointer over here because I'm actually using desktop. So it's just a mouse that I'm working with. I don't have a touch a pen. Okay, so we have this geometric model over here, and the geometric model surfaces from basically the initial concept of an idea. So it actually stems to the point of why we need to actually come up with a design. So the reason why we are coming up with a design is, can anyone tell me why do we design something? Anybody?
To create products.
Okay, to create products. But before wanting to create products, what was the need to even create that product? Anyone? Why do we need to create those products? Are you all there? You can type in the chat also if you all want to. So why does anyone want to create products?
To fulfill the demand.
To fulfill the demand is one reason. And the demand comes
Because
to,
there is a problem.
yes, to solve a problem, like how Irfan Hafi has said in the chat, right? To solve a problem. So initially what we are going to have, we actually have a problem, and due to that problem, there is a demand based on that problem, and hence the ideas actually spring up to in order to fulfill the demand to solve that problem. And once that happened, then we actually move on into analyzing. Wait, a lot of y'all are joining. You're required to actually join using your SISWA ID. So there's no need for me to admit you all when we use Microsoft Teams. Okay, so try to get your SISWA ID working. So once you have the problem, right? So then we come up with the design. So what do? We have a problem, we have an idea to solve that problem, but it's all in the head, right? So in order to make it real, to realize that entire situation, we actually come up with the geometric model. So what is a concept in our head? It's transferred into a virtual concept through the geometric modeling method. Okay. And from this geometric modeling method, what do? We analyze the design. Okay. So we analyze the design for multiple factors, okay, to see whether it's conceptually working, functionally, passable, and then we check its structural integrity to its strength and all those things, and then check whether the working principle works, and multiple aspects, right, are looked into. And when all these things passes through, only then we actually produce the product. So that's what we actually understood from chapter 3, right? The whole idea of modeling, design, right? Once it passes through the phases of design, then only it goes into the phase of production. So this is the difference between a conventional design and a computerized design, where the computerized design will make way for the production of a product where it is expected that there should be no error. So if at all any error happens, it's going to be a very minimal one. So this is why we need a geometric model. So if you get any questions on why do we need a geometric model, right? So this is how you need to answer this. Okay, just a minute. Okay, now the next slide, right, tells us of the functions of geometric modeling. So this functions of geometric modeling, basically what this does is it describes geometric model functions, and in your geometric model, what are the things you can do? Okay, so under design analysis, so this is not talking about the structural integrity analysis yet. It talks about your model itself, the analysis of the model or your design. You can actually check things like area, volume. So this kind of capabilities and functions are there in all software. So we are using CATIA, so we'll learn through that. You can evaluate mass and inertia properties. You can check interference in assembly, right? And then you can analyze the tolerance, right? Build up in assemblies. You can analyze the kinematics, the mechanics and robotics. And then you can analyze the mesh generation for finite element analysis. So it's in finite element analysis that we actually analyze the structural integrity. And with the geometric model, if you look at the drafting section, you can look at the cross section of the model. You can imagine this model. You can actually look at the cross section, hidden line, surface removal, shaded image, dimensioning. So these are all the aspects which you can directly look at. So many of you all are coming in through outside accounts. All right. And then under the manufacturing side, you can actually classify the model. You can plan the process. You can do NC code generation, robot program generation. So these things are all possible through your geometric model when you have a full proper geometric model. And then under production, for the purpose of production engineering, you can generate the bill of material table. And after generating the bill of material table, you can actually create your material requirement table, all right, to the process of MRP, right? Manufacturing resource requirement. So what is this manufacturing resource requirement? We want to know what are the resources required, right, for your model, from the raw material to the entire production capacity, okay? And you can schedule the processes in batch. Let's say we're going to actually do a new batch every 3 weeks once. So how do you bring in the material every 3 weeks once? And all these concepts can be looked into. We can also inspect and quality control the model through, like what we learned in chapter 2, CMM machine, coordinate measuring machine. So these are one of the inspection machines to identify errors in the model in dimension. Then we have all this virtual reality machine where, it can actually do like an X-ray scan to see, if there are defects in the model itself, even internally. And then we have like, augmented reality. We can just identify things, you program it to identify like barcode, labels, many things, all right? And we can always compare this with the produced part. We can compare the produced part with the design we have made. So geometric models are divided into two. We would have had an overview of this in chapter 1, right? So chapter 1 actually covers an overview of all the chapters, right? So we would have heard of this. There are 2D models and there are 3D models, right? So the three principal classification of a geometric model is, you can see this tree, whereby you have the line model, which is actually the wireframe model, right? So it's a wireframe model, meaning to say there is no solid inside here, right? There is no surface. It is just connected by mere lines, right? Wireframe, okay? And then you have the surface model, which we have, I'm sure you all would have already heard from Dr. Salbia's class, right? This model does not have the solid. It only has surface covering. So you can see surface 1, surface 2, surface 3, all right? What's the difference between a surface model and a wireframe model? A wireframe model gives us the beginning step of a 3D vision of the layout, but it can become ambiguous. Like if I look at this part over here, okay, so you can see over here, this section over here, it may look like, this part is going on to the back. We don't know whether this is in the front or in the back. So a line model can create ambiguity, okay? So in a surface model, the ambiguity of the 3D representation is removed, so you can have a better presentation. And finally, what we all are looking for is the volume model, all right? So it is in the volume model that generally analysis makes sense, all right? Because we can actually capture the entire effect on the entire solid. So we have like volume 1, volume 2. So this is how you all are designing in CATIA based on volume model in general. So here we will go through, I'm going to recap what we saw in chapter 1. So I'll go through this faster, okay? So we have the wireframe modeling system, which is a visual presentation, like I mentioned earlier, for a 3D or physical object, all right? So basically what it does, all right, the wireframe modeling system differs from a 2D drafting. So the 2D drafting looks like a wireframe also, but it's two-dimensional. In a 3D situation, the coordinates are represented by the X, Y, and Z coordinates. So hence you have the 3D presentation. So the wireframe term comes from designers using metal wire, or you know, in your kindergarten days or primary days, you're required to build a model, you'll use matchsticks and this and that. So that's how the concept developed, all right? So to actually you know, give you all an insight on how even in the virtual environment when they were programming the software, this is how the concept developed. So the shape is defined by a collection of point of vertices, right, which is bounded by the edges. So it uses geometric entities like lines, arcs, curves in order to create the design. So these are examples of a wireframe model where you can actually get a pretty good representation, but you don't know, you know, you see, like you don't know what is inside, outside, like that. So the computer has no knowledge of the surface shape between the edges of what is solid and what is not. And you can see now how this is visually ambiguous. This is what I tried to point out. You don't know whether this is actually on the outside, all right, of this area, or is it on the inside. So wireframe model it's rather useless in that sense, all right. And so it tends to be not realistic, ambiguous, as I mentioned, because you can't interpret it. And most importantly, you cannot compute, right, mechanical property information like mass property, volume, mass, moment, and everything. Hence, it's not useful for analysis. Therefore, sometimes it's seen to be incorrect, right, incomplete, and definitely not fit for manufacturing purposes. Now, the advantage it offers us is it's easy to construct. Like when I ask you all to do the mini project and I say, okay, now I want to see what you all are planning. So just give me a sketch. So your sketch is actually your wireframe. So you can just construct and try to tell me, you know, this is what it looks like. So it's economical when you want to pass a message, especially in the beginning stage of a project. And it's often used for previewing objects in an interactive scenario, all right, in low-end designing. So you can draw some impossible solids with wireframe. So it's an example of a wireframe. And now we move on to surface modeling. So surface modeling is constructed essentially from different surfaces, all right? Like planes, rotated curves, and ruled surfaces, all right? And we also have very complex surface, which we will see. So the aim of surface modeling is to completely define the surface form of an object, right, in such a way that the computer can actually calculate the X, Y, Z, and coordinates. So I will explain this further in the following slides. So some surfaces, you cannot define it by analytical techniques like car bodies, ship hulls, die cavities, right? Decorative surfaces, where the surface is not a simple shape like a sphere or an ellipsoid or anything like that, okay? These surfaces have multiple combinations, okay? So how then are we going to actually find out? How we're going to find out is these surfaces are usually modeled not from a basic shape like a circle, right? Is modeled from a center point and a radius, all right? A center point and a radius. And when this is turned into 3D, when it's rotated, so you will get like a sphere. Where else? How are complex shapes like this, you know? You can imagine if you have, you know, a 3D shape like this. So how are they modeled? They are modeled through a series of control points and other boundary conditions, okay, which specify the shape. So a few control points and boundary representations. So the common surfaces used in the CAD system are like ruled surface, Bezier surface, B-spline, and NURBS. So what we are going to actually learn is we are going to learn Bezier calculation. Why are we actually inserting this into your syllabus? so that you can appreciate and even understand how surfaces are actually drawn and what is the complexity behind building this software. We take it for granted when we can just generate a cube, a cuboid, you know, when we do design. So they are not just very easy things. A lot of effort has been put in to develop all this, right? To ensure that it's easy for us to draw. So these are different surface models that you would have actually, you know, seen so far in CATIA, right? Like this is actually a sweep. You have a cross section over here and it's swept through this trajectory. So this is actually a different type of surface model. This could be a revolve model like that, okay? So we come into the classification of surfaces. So we have three types: planar, which are flat surfaces like polygons, polyhedras, right? They are planar surface which you can extrude into three-dimensional surface. Okay, and then we have curved surfaces like single curve and double curve. So single curves are like cylinders. You will understand, right? A cylinder is like this. Of course, the bottom is not flat, it's round also. So the top part and the bottom part is flat and this area is curved. So these are like single curves. So same thing with a cone, for instance, single curve, okay? And then you have double curve like a sphere. So you have one circle like this and you have another circle like this. Okay, pardon my drawing, but you know, one circle and another circle which creates that sphere. Ellipsoids, paraboloids and everything. So all this are ruled surfaces. And then you have free-form surfaces, which we call cone surface. And how are these free-form surfaces formed? Through all these formulations: B-spline calculation, Bezier formulation, NURB, fractals. So we call this lofted surface. Okay. So these are the various types of surface used in geometric modeling. Examples, right, of single curve, you can see now. This is planar and you have a single curve, all right? Only one curve over here, one curve. Although it's drafted, but it's still a single curve. Then you have double curve, okay? One curve this way, another curve that way. One curve this way, another curve this way, okay? And then you have translation and revolution, right? You have basically few points. This is what we call the multi-section solid, right? One planar, two planar, although it's circle, but it's flatter, which is actually swept across a cross section, which gives this shapes. So how are this creating of the surfaces done, right? So the CAD packages, right, are basically equipped with the ability to create all this kind of surfaces. And why? Because it's basically a niche in the market, an absolute need. So if you look at any products you hold in general now, they all have some form of surface representation. So you can see now I'm showing you, this is supposed to be a pen holder, right? And even this, you can see the surface is curved over here, all right? So it happens even in the most basic stuff, okay, which is very cheap, also needs curved surfaces in design. So earlier on, we discussed the types of surfaces where we had planar surface, curved surface, and free-form surface. Now we are going to discuss the resulting surfaces, which is also classified into three. Okay, earlier on are the types of surface and now the resulting surface from those types. Okay, so the resulting surface, we have generic, freeform, and derived. So what are generic surfaces? So generic surfaces are created by sweeping a generator curve along a vector or an axis. So anything which is, so only the generator curve influences the form of the surface. So the types of generic surface that we have is tabulated cylinder. So if you have like a cylinder, right? So what do you do in your CATIA? First you do is you draw a circle and you extrude, and then after that you give a height to the circle. So you can also use the sweep command, draw a circle and draw a trajectory line. So if the trajectory line is straight, then you get a tabulated cylinder. If the trajectory line is, let's say, curved, then you will get what we call a curved cylinder, like a pipe. Okay, so that's the concept, tabulated cylinder. So sweeping a generator curve along a vector, right, which produces a surface tabulated. So the magnitude of a vector controls the size of the surface. And then you have surface of revolution, shaft or revolve, where if you have one particular product, okay, you have an axis. If you revolve it based on whatever degree which you state, and then you will get a product like this. So as I said, pardon my drawing, something like this, all right? This is the resultant of this. So this is a revolved surface. So here you can see curve and the directrix, all right? You have a basic curve with the direction, and then you have a basic curve like this with the same direction, this type of curve with the direction, okay? Tabulated cylinder and surface of revolution. Next, we have free-form surfaces. So what are free-form surfaces? It uses more than one curve to create a free-form surface. So the surface is modeled through a series of control points and boundary conditions. So there are 5 types of free-form surface, and the first one is a ruled surface. So what is a ruled surface? It's created from 2 or more curves that form opposite boundary. So you have one curve here, another curve here, and the way the curve, folds, it will form the boundary and hence form the surface. Okay, so basically it's just commanded by 2 curves. Okay, so that will form the surface. The lines in between will just follow straight through. The next type is a surface patch. So that is formed by an enclosure of 4 areas. So how you can do this is, I'm not sure if you all can see, if you have a paper, right? If you have a paper, so you can see a paper is actually a boundary of 4 corners, not 4 corners, 4 edges. So if I want my paper to, you see now, ripple like this, okay? So what happens when my paper ripples like this? It basically just means that each of my boundary is being curved, okay? So I'm actually trying to curve, you see the one I'm holding here, one boundary is trying to be curved, another boundary. So all this curving over here is creating one kind of ripple on the surface, okay? So this is what we call a surface patch. The surface forms based on the enclosed area. Then we have net surface, where it is formed based on a network of curves, multiple networks of curves, okay? And then we have the swept surface. So the swept surface, you can, like I showed earlier, we have a cross section and a guide or trajectory curve like this. And then we have the loft surface. So swept surface, maybe you all would have seen in the lab already. Maybe some of you would have gone through the lofted surface in the lab as well. So the lofted surface is such that you have different cross sections at different planes, and you can merge all this cross section at a based on a guide curve. So the guide curve can be straight or the guide curve can be curved. So for a straight environment, you will get like this, a formation like that. And for a curved environment, you get a formation like this. Okay, so the guide curve is limited by the surface boundaries. So these are the 5 types of ruled surfaces. Okay. Next, we come to the third one, which is derived surface. So what is a derived surface? It's created from one or more existing surface. Okay. So one example of a derived surface is an offset surface. So you would have seen this if you had actually created reference planes. It is an offset surface. Or any type of curve can just be offsetted. Or it's more like copying the curve over, okay, at a distance. Another type is a fillet surface. So how do you get fillet or corners which are rounded? Basically, the idea is you need to imagine that a ball is moving around that corner, a ball with a specific radius. So this is fillet surface. So an offset surface and a fillet surface is called derived surface because it's obtained from an already existing surface. So now we come to Bezier curve. I will only explain Bezier curve to you all just as the intro, and we will look at the calculation in the following class. All right. So basically the concept of a Bezier curve is it is from the free form curve. So it actually deals with complex curves, and curves, many curves put together would give you complex surfaces. Okay. So to obtain a more free form design for an aesthetic surface that satisfies the requirements or the demands made, right, by the shape that you want to create. So this was actually achieved by using the Bezier curve, named after P. Bezier, and he's the designer of the French car company Renault, right, who invented this procedure way in the 60s. And that time, of course, it was a lot more less complicated to as it is now. So what it does, it uses the vertices as control points, right, to approximate the generated curve. So the points, Bezier curve. Okay, so let's say we have a curve. So what is different about this curve now? When we have a curve, this curve is generated based on control points. So you have control point 1, 2, 3, 4, and 5. And each of this control point will have, a coordinate x, y, and z. Okay, depending on 2D or 3D. So this will be x1, y1, z1, and then x, 2, y2, z2, and etc. All right. And each of these control points are joined by what we call this control polygon. Okay. So the curve touches the first and last control point. Now, how do we change the shape of the curve? By tweaking these control points. So as you can see now, right? We have this, and as we move this control point from here to here, you see the shape of this curve changes from this to this. So this is how we tweak the curve. So basically the curve is formulated by all the different control points. So changing the position of individual control points will alter the polygon, which in result will alter the curve. So the more the control points, the higher the flexibility of the curve for a Bezier curve. And this is how a Bezier surface is formed, because you have polygon surfaces, control polygons to tweak the surface. The next one is what we call a B-spline curve. So what is a B-spline curve, right? If Bezier is considered as a single curve controlled by all the control points, right? So what happens as you increase the control points, the polynomial, so this is where the mathematics comes in. The polynomial representing the curve increases. So polynomial means to the power of 1, to the power of 2, to the power of 3 in your equation. All right, quadratic polynomial, cubic polynomial, and then we go on and on and on. So the more the control points, you will realize when I go through the calculation, the polynomial of the equation itself will increase. So to reduce this complexity, the curve is broken down into more segments, all right, with better control exercised at individual segments. Due to this concept, the approach of B-spline was brought in. So what is the approach of B-spline? If you can see now, what is the difference is the control points 1, 2, 3, 4, 5. Okay, they are all touching the curve. Okay, and when they are all touching the curve, okay, when you have your curve over here, okay, let's say you want to move this control point, it will not affect the entire curve. When you tweak this control point to this, right, what happens is you only change this section and this section, because this control point is linking to, and this one will remain the same. Whereas in Bezier, as you tweaked one, because it's a control polygon, it kind of pulled the curve over. Whereas this one gives more of a localized modification. So why was this done? In the interest of bringing down the complexity of the equation. So the B-spline equation as a beginner itself is more complex, but as you increase the complexity of the curve, then it is easier to modify the equation. Okay, so this is the difference between B-spline and Bezier. What are we going to learn? We are going to actually learn the formulation of Bezier curve. Okay, so because Bezier's formulation is a simpler one. All right. So this is basically Bezier formulation, and then I've given all this, so we will go through this, all right? So I'm skipping that because we're going to go through it in the next class. So the next that we have over here is the application of these surfaces. So why are these surfaces applied? To basically create photorealistic images, all right? If you look at anything from your car to your, your computer, your TV, your pen, your phone, anything that you hold, right, already has surface rendering. Okay, and what happens when it has different surfaces? What happens is you can see, right, with the different surfaces, what happens is the light reflects in a different shade. So the different angles, not a one flat angle, huh? The different angle allows different rendering capabilities. Okay, so you can actually assign different light sources, translucency, opacity, and everything to create beautiful images as shown over here. Okay. Okay. We spoke about wireframe modeling, surface modeling, and now we move into solid modeling. Excuse me, let me just drink some water. So solid modeling is what we are practicing in our modeling technique in CATIA, basically, all right? A solid model is a computer description of a closed solid, right? A 3D shape represented by a data structure, right? And a solid model, right, has data which can be analyzed, right? It is a 3D, it has data where you can actually apply 3D material, all right? It is complete and it is not ambiguous. So it is composed of combinations of primitive objects, all right? And as I mentioned, it is completely clear and it's physically realizable and modifiable. So a solid model is always open to further modification by Boolean combination with other shapes. So solid modeling technique is particularly suited to the automation of many manufacturing and analysis tasks. So it is with the solid model that we can even get shapes like this or any shapes that you're drawing. We can mesh them and analyze them. So we have two types of solid model. We have the CSG model and the boundary representation model. So let's look at what are these. So what is the constructive solid geometry model? The CSG model representation uses what we call a tree structure, often called a CSG tree, to define a solid model part. All right. So this comprises of Boolean combinations of solid primitives like blocks, cylinders. So when we use this term primitives or attributes, earlier on we were discussing 2D, right? Like circles, arcs, triangles. So the 3D version of it would be like blocks, cubes, cylinders, spheres, cones, like that. Okay. So the CSG method uses what we call the Boolean operation of union, difference, and intersection. So union means add, difference means subtract, and intersection to combine different shapes to form, right? These are all the different shapes, all right, modeling primitives that we have to form our multiple shapes. So you can see over here now, you have design 1, design 2, design 3, and design 4. Okay. So in design 1, 2, 3, and 4, how was this design created? It was merely created by first modeling only two shapes. We modeled a square and we model a circle. This is a 2D. Yeah? So when we actually use this union command, you get this shape. You use subtract or difference command, you get this shape. If you use intersection command, you get this shape. Similar to this. You can see now, this is the initial. So if you have union, okay, you get this. Subtract, you get this. And intersection gives you either this, the top part, or sometimes even the bottom part. It depends on how you intersect, and it depends on what you actually state as the base model. So usually when you do this Boolean operation, you must define the base model, and the base model is generally the first shape that you draw, okay, in your computer. So if you tell me now, why do I need to go through all this? I would say you need to go through all this if you want to avoid doing 4 different types of design, right? Let's say you want these 4 outcomes. So you might as well go through a Boolean operation instead of drawing this model first in CATIA and then drawing another time. If I say I want this shape now, okay, you have to redraw. I want this shape now, you have to redraw. But if you know and you can identify, you can actually one-stop center, you can do all this, okay? Now, this is an example of why Boolean operation is needed. useful, okay, when we want to mix and match organic shapes with inorganic shapes. In this case, this helical spring is an inorganic shape where you can create its design. The human skull or the head is an organic shape. You cannot design this in CATIA. Simply impossible. Can someone tell me why it's simply impossible? I'm talking about designing it in CATIA. And when I say simply impossible, I mean to design it exactly like this. So can anyone share your opinion? Are you all there? Why do you think it's impossible? The human skull.
Because it use surface modeling.
Okay, because it requires surface modeling. Not exactly. We can do surface modeling in our softwares. Anyone else? If I asked you to design, can you do it? Because we have no exact dimension, Najmi says. Correct. All right. How are you going to measure this? You can try measuring the nose, you can try measuring the mouth and here and then. That's finally, if you're successful, you measure my face. And then I want to draw your face. Oh dear. Can you imagine? My dent in my eye, my nose bridge, my this. And can I say I want to modify here a little bit here from Madam's face? Cannot. We all have completely different shapes. So organic shapes are such that they are unique and individual to themselves. Okay. So usually how are organic shapes actually designed? They are basically scanned, and the scanned image is actually imported into the software as a 3D model. And if you want to have a combination of an organic and inorganic shape, or a combination of organic and inorganic or whatsoever, like in this case, you imagine you want this kind of design, right? So this can be done with Boolean operation, where you can get very unique features obtained and drawn out. All right. So Boolean operation is basically useful when you want few different types of designs, which you can actually, obtain through a model, two models, without having to draw different models. So it has its ups and downs. All right. So this is the concept of the Boolean operation, like you can see over here. All right. The Boolean operators, okay, where you have a block and a cylinder. So if you have the union command, you get this. You have the difference command, you get this. You have the intersection command, you get this. So in this slide, I have added actually YouTube video on CATIA on Boolean operation. So let's see, what's the time now? 11:09. Okay, let me see how quickly I finish. If I finish quick enough, then I can actually give you a video on Boolean operation. Okay, so this is the Boolean operation. So the concept is such that how does this Boolean operation happen? You can see now in 2D, let's say you have a circle and a square that you're combining, right? How it actually identifies the difference is it cuts off at wherever the boundary is crossing. So if you all would have used the trim function in CATIA, right? The quick trim, the rubber icon. So it goes by the same concept. So wherever there is a intersection between the two parts, that's where it notices its boundary order, okay, to form the different shape, like you can see over here, all the different examples given. Okay. So this is what we call a CSG tree, a tree which illustrates the formation of a final model by combining, subtracting, or intersecting different shapes. So you may be getting this kind of questions in your exam where you are given a block and they will just say, please construct a CSG tree, for instance, to actually assume this final shape. So you can get your basic, you have to decide which is your basic design first. So let's say the basic design is the block. Then I need to add another rectangular block, okay, to get this union. And then I need to get a cylinder, okay, put in over here, subtract, so that I get this. And then a block over here to subtract. And then finally 2 cylinders to subtract, so I get my final shape. So it actually tells us step by step how we move on. Okay, so this is a CSG tree. So far, any questions from you all? Anyone with any questions so far?
No,
Okay.
madam.
Okay, so if none, so basically Boolean operation is a binary tree. CSG tree is a binary tree consisting of geometrical primitives and transformation and symbols representing the Boolean operators. So the database of CSG model stores primitives and Boolean operations only. Okay, so only of those models. So the CSG method enables one to build complex shapes quickly, but only within the limitation of the set of primitives available. So you can only build this shape based on the primitives you've added, or you can only build the shape based on primitives. So what is the primitive? We have one block, we have one cylinder, that's all. So you can only play around building these things because it uses a concept of modeling. Now, the second solid modeling concept is what we call the boundary representation or BREP model. Okay, so what is a BREP model? It's a type of solid modeling in which faces are combined to create a solid model of a part. Okay, so a solid model is represented by an enclosing surface and describing its boundaries, and faces are presented by the bounding edges and vertices, or what we call points. All right. So the geometry of the object can be described by its boundaries, vertex, edges, and surfaces. So to keep the long talk short, what does this mean? It means in boundary representation, if in Boolean representation, what we did was we first need to build shapes or we need to import shapes. Whereas in boundary representation, how we need to do is we need to create basic shapes. So let's say, like I want to draw a square, so I have to draw 1 line, 2 line, 3 line, 4 line. Okay, or if I want to draw a cube like this, first I need to draw a square. All right, a boundary of edges, vertex, all right, connected by edges, which creates a bounding surface, and this surface later swept through a trajectory will give you this surface, this surface, this surface, this surface, this surface, and this surface. Okay, so this is how boundary representation is done. So these models are initially created with boundary representation, if you would have realized. Okay, we don't have these primitives in 3D in our software, at least not that I know of yet. But in 2D we do. You notice in 2D you can straight away draw a cuboid, you can straight away draw a square, you can straight away draw a polygon. So the 2D formulation is already kept, whereas a 3D formulation is not made yet. So you can imagine a 3D formulation of a cube means as soon as you say you want a cube, what the dialog box will ask you to input is what do you need for a cube? You need the x-axis, the y-axis, and the z-axis distance. That's it. You give this 3 distance, you will get a cube. You want a cuboid, then you can change, of course, x, y, and z. And then if you want a, let's say, sphere, for instance, what do you need? You need like, the major axis, one radius this way, another radius in the other direction, okay? And it's revolution, then you may get a sphere. So this kind of things are possible as soon as you actually draw quick models. That means it's being done by the Boolean concept, all right? But before the Boolean concept is made, every shape is actually formed through a boundary representation. Okay, so basically boundary representation basically means you're building your 3D model based on boundaries. Okay, so that's the idea. Okay, so can you all tell me now, in the Katya that you are doing, are you all using Boolean representation or boundary representation? Boolean modeling or BREP modeling? What do you think? So far that you all have done 3D modeling.
Boundary representation.
Yes, we are using boundary representation. Why? Because we are actually drawing from boundary points, edges, boundaries, surfaces. Okay, so basically, due to the need of engineering and manufacturing support functions like drafting, analysis, and all those things, you need a detailed data structure. And that is highly available based on BREP representation. Okay, so we can't always rely on the primitive Boolean operator because it limits us to that particular shape, whereas in a BREP you are more free in making your design. Okay, so the Boolean operation is always included in most BREP modelers, and our commercial solid modelers are BREP types. So you will see in CATIA you actually have the BREP function present. Okay, so the application of solid model. Why do we need solid models? Because we want to obviously visualize how a model looks like. We want to calculate mass property. We want to do assembly, and then we want to check whether there's interference in our assembly. And then we want to draft our model so that it can be sent as a production documentation. We want to manufacture our model through rapid prototyping or any other manufacturing process. We want to do structural analysis to see the integrity of our model. Is it strong enough when it goes to stress analysis, strain analysis, heat analysis, right? We want to analyze the mechanism within that analysis to see if it's full and fine. We want to analyze tool design. We want to see we want to generate numerical control codes so that we can automatically manufacture through automation instead of manually key in. From your model, the codes are generated from your CAM software, and straight away we can run manufacturing. We want to be able to use the robotics aspect, simulate and see how your model looks like, and all these factors. Okay, so you should be able to elaborate and discuss these points. Okay, this slide is actually it should be in the busier part. So basically what it's trying to actually discuss over here, this slide, right? We spoke about classification of surfaces. This is a repetitive slide. And when the surfaces combine and meet together, you will get, classification of, earlier on we described about curves, all right? So when the curves combine, right, in a mismatch, you will get surfaces. So that's basically the point it's trying to pass. So the surface connectivity, all right, if earlier on in Bezier, we are going to look at curve. So the surface connectivity also takes the same concept, all right, as the curve connectivity. Okay, next we come to the concept of hybrid modeling. So what is actually hybrid modeling? Hybrid modeling is what I just now tried describing to you all in the Boolean aspect. It means combining digital shape sampling process with the power of CAD, all right, to provide an innovative solution for parametric reverse engineering of complex parts. So when we use this term complex parts, it could mean a car bumper, it could mean a car hood, it could mean the entire car, it could mean my skull, my bone, right? Biomechanical engineering now reverse engineers the bone. Each of our bones has a different shape. So we bring in, import the bone, then we can study all those things. So these are complex parts, right? How do we reverse engineer them? We use digital shape sampling process method, which converts 3D scan data into digital model for all these purposes. So once you have a cloud sample of your data, multiple data as you digitize, imagine you have a part and you collect, it digitizes means it takes coordinates from every point. It comes in, imported, and then you form the surface and create the solid. Once your surface is already formed, then everything inside should be assumed to be solid. Okay. So the combining advantages of the DSSP featured with solid modeling provides what we call a hybrid modeling. So it simply means when you import a product in, from that import, we can create something. Like I tell you, okay, now please analyze for me the Perodua car bumper structure. So when I say that to you, you'll be like, madam, I'm supposed to design the whole thing, is it? I said, okay, if you want to design, go and try designing. So you go to Perodua, let's say Myvi, and you look at the bumper and you're trying to measure. As you are measuring, you will realize how I'm going to get this curve, how I'm going to get that angle. It's all complex, because usually these bumper designs, hood designs have a lot of surface. So what you can do is you can digital shape sample it, right? Digital shape sample means it kind of scans the entire data, coordinate data. It exports into your software and it will form the entire surface and solid. So now you have a bumper imported in, the full Myvi bumper. And from that bumper, you can start making designs. You can actually cut out, more holes, make extra extrusions, and then study From that bumper, if I cut out a hole, I make extra extrusion, is it more solid? How is the analysis? Is it, more rigid? So these things can be done. Then designing it from basic or scratch. So hybrid models actually fix this kind of limitations, right? So in hybrid modeling, the point we want to pass is reconstructing a complex shape in CAD takes a long time. And there's no guarantee that the finished model will be accurate, right? Like how we said, our face, our skull. So in some cases, it's almost impossible to use a feature-based approach to actually bring in the design. So this is where the hybrid modeling proves to be useful. So the applications for hybrid modeling are you can capture physical designs and prototypes which are already made. You can reproduce legacy parts and toolings where there were no data. You want to go to the museum and get all these legacy parts, those ancient days where you don't have CAD data, no drafting data, no data at all only. Okay, so you can actually reproduce by just scanning. You can replicate complex and organic shapes like I explained earlier. You can prepare as built models for CE application. So in the automotive industry, the aerospace industry, they don't redesign anymore. They just digital shape sample, reverse engineer, and start analyzing from there. You can mass customize unique components like dental applications, hearing aids, because they have specific shapes. And you can preserve historical and cultural artifacts because once you bring in, you get the CAD data, you can get your CAM data, you can get your drafting data, and hence that part is actually reproducible. This is an example of a modeling an impeller, which looks complicated. We scan the impeller, and when you scan, right, you can see over here, when you scan and come in, you can see, this, let me change my color. You can see over here, these yellow areas, right? So these are areas where the data, when you scan, it wasn't scanned in fully. So what happens is once you get this kind of data in, you extract curves and datums. Okay. So in this area, what you do is, in this boundary, what they try to do is they will trace this boundary out and, okay, they will patch this boundary. That means make a surface form. Once the surface is formed, then they will extrude the surface. So you would have realized by now in CATIA, when you are extruding solid into a solid, what happens? It merges. So it doesn't matter. Okay. So that's the same thing we're going to do. Extrude a solid into a solid. So it merges. And then like that, you will trim off and you will see you'll get a smooth surface. You see all these parts have been settled. So once you do that, right, then this particular model, actually you can see now this is how they get the surface actually extended. The model becomes fit for analysis because you can mesh and you can do anything else with it. Okay, so this is an example. So the advantages of hybrid modeling: it uses 3D investments, it takes advantage of existing modeling systems and skills of CAD, right, to enhance and work on rapid surfacing. It helps to quickly create new designs, right? Hybrid measuring and modeling approach greatly reduces the amount of time needed to copy an existing design, like I mentioned earlier already. Okay, we can just quickly import and generate, which can be done within days in compared to weeks if you want to try to model it. You can produce native parametric CAD geometric parts, right? And you can generate very accurate results through digital shape sampling instead of trying to model it step by step. Okay, so in this case, you have less data loss and everything. All right, so we are done with the first part of chapter 4. Do I have any questions from you all?
No.
No questions, huh? Okay, if there is no question, you just wait a few minutes, a minute or two, just take a 1 minute, 2 minutes break. Let me check and see if I have my Boolean video in my UFuture, okay? So I will just stop the screen sharing for a while. Okay, and so let me check out the UFuture. If I've already made a video, then I will just play that video. So again, I just like to let the other classes know, if you want to access my folder, you can. There is a password to lock it, right? I believe I shared did I share the password with you all before this? Anybody?
Yeah, MEC 435 online, right?
Yes, yes. Okay. Not the 8B class, but then the other classes. Okay, wait. Let me see if I have Boolean over here. Friends, crafting. So this is solid combine. Okay, so I do not have Boolean. So what I can do is, just a minute. Okay, so for today's class recording, it's over. So I will stop the recording and then I will actually show you how to work on a Boolean operator right after this right now. So just give me a minute. Let me open up my CATIA.